Okay, if you can turn to your quiz review packet.
Yeah. More like, it's nothing.
Does anyone not have the quiz review packet?
Actually, so many times. No. I haven't had the essay today.
Okay, page 2. Let's try number 6. So number 6 is first derivative test. If you feel pretty comfortable with this, you're finding f prime, setting f prime equal to 0, creating your slope sine line, and then getting your plus and minus slope behavior to show up on your slope sine line. And then looking at the arrows, looking at how the arrows are rising and falling, we should be able to identify our relative max and relative min. And also want us to practice writing out our because statements. Okay, so this problem is only asking for your relative extrema. So from our function, we can find our first derivative. From our first derivative, we can set equal to 0. Factor out of 3, continue factoring. We set each part equal to 0. We get x minus 9 equals 0, x plus 1 equals 0. If you set the coefficient equal to 0, it won't make any sense. There's no variable there. 3 equal to 0 is not a solution. So only 9 and negative 1. And then we choose values in each subinterval. Here I chose negative 2. Here I chose 0. Here I chose 10. Inserted them all into the factored form of my derivative function. All right, negative 2 in for x. I get a negative times a negative, which is positive. I plug 0 in. Negative times positive is negative, which is negative. Plug 10 in. Positive times positive is positive. So the arrows are helpful. Positive slope for a positive sign, a negative slope for a negative sign. So the graph is rising and falling. And you can kind of imagine that there's going to be a relative maximum because this graph is going to hit a hill of the graph at negative 1. And then at 9, the graph will hit a valley. Okay? And our relative max and relative min, make sure that we know how to write our because statements. I see some students do a couple of things here. They would say because there's a sign change. That's not clear enough. Make sure that you specify what you're talking about. Right? Or they would say because the graph sign changes, or no. So if you use the word it or graph or sign, we want to be sure to specify what we're referring to. Okay. All right. Any questions with finding the relative max, relative min, and also our because statements? All right. Try number 7. Number 7 is concavity. So that is down to the second derivative level. So we're going to create our second derivative sign line. It's going to feel a lot like the process that you did here. It's just at the second derivative level. But instead of the plus and minus indicating positive, negative slope, the plus and minus will now indicate concave up or concave down. Okay, try 7. Okay, so number 7, we have to make our way down to the second derivative level, set that equal to 0, solve for x, we get x equals negative 1/3. Negative 1/3 now gets placed onto our f double prime sign line. Then we want to pick values in each subinterval. Here I'll choose -1, here I'll choose 0. You can choose other numbers as well. I just am picking numbers that are closest to 0 if possible. So -1 into my f double prime. -6 plus 2, that's negative. So my negative second derivative is not negative slope, it's concave down. So I use a upside down U to indicate what the shape of the graph will look like. That's a reminder that we're dealing with curvature information here, concave down. Plug 0 into the second derivative. I'll get a positive number, so concave up. Now, there has to be a change in sign in order for our critical point to be a point of inflection. So we want to make sure, I see some students say because f double prime of x is equal to 0. If you say that, it means it's still a candidate. It's not confirmed that it's a point of inflection until we establish that change of sign. So f double prime is equal to 0 is not strong enough of a statement. We want to be able to say that f double prime of x changes signs. And then concave up and concave down, the reasoning is because f double prime is greater than 0 for concave up, because f double prime is less than 0 for concave down. And how did I get to this 7.074? Yeah, into the original, right? So anytime I'm looking for a point, whether it's a relative max or relative min, if I ask you for the full order pair, you involve the original function. The original function will give you a physical location on the graph. All right, are we okay with 6 and 7? I think these are the problems that are most straightforward. Creating the sign lines and just pulling information from the sign lines. So hopefully we feel okay about that. All right, next up, number 8. Number 8 says use the second derivative test. I think this is a cause for confusion because this does the same thing as the first derivative test. So why don't we do this just for comparison purposes and just so that you can kind of see exactly the difference between them. Let's do this using first derivative test, and then we'll do using second derivative test. So you can kind of, obviously on the quiz, if I ask you for second derivative test, I'm just looking for the steps for second derivative test. But I think it's maybe good to kind of have some perspective as to, that you have two different ways of doing it. They both will end up in the same result, but the steps are, the way we get there is a little different. So we're comfortable with first order tests. So let's see if we can find relative max, relative min with this process. Minus 10. Oh, sorry, there is a typo on my worksheet here, on the worksheet I picked up. It's not going to factor nicely if it's minus plus 20x. It should be minus 20x. Sorry about that. If he hasn't changed number 8, it should be 2x cubed minus x squared minus 20x minus 10. So my critical points are -5/3 and 2. I'm going to plug negative 2, 0, and 3 into my f prime sign line here. So -2. I'm going to get negative times a negative, which is positive. Plug 0 in, I get positive times negative, which is negative. Plug 3 in, I'm going to get a positive times positive, which is positive. Now, using the arrows, we can tell where our relative max is. We have relative max at x equals -5/3, and relative min at x equals 2. Okay, so this is first derivative test. This is not what the problem is. Well, this is not the process that this problem is asking for, but I just want us to kind of have this where we feel comfortable with this process. We know what the answer is supposed to be. Let's use the second derivative test and see how that process is different, but will still get us the same result. Okay, so initially the steps will feel the same. You're still finding the same candidates, so we should still be involving -5/3 and 2, but rather than using sign lines, we're going to go through a different process. We're going to use the second derivative function to test these numbers. Okay, so right now we don't know whether these are relative max, relative min. We're doing this without the sign line. So the way we test these now is we're going to use the second derivative function. So let's find f double prime of x. Okay. What's the second derivative function going to be? Power rule gives us what? 12x minus 2. Okay. Do we set this equal to 0? If we set this equal to 0, then we're looking for something else, right? Then we're doing what we did for number 7, which is looking for points of inflection, second derivative sign line. So we don't want to do that, right? We are using the second derivative function, but we're not setting it equal to 0. That's the test for concavity, right? So what we're going to do is we're going to take these numbers and we're going to plug it in for the x of f double prime. We're going to gather information about it. So f double prime of -5/3 is equal to I get negative 4 times -5, which is -20. -20 minus 2 is -22. Now this number is a little abstract. This number is not, we're not going to be able to see what that, we're not going to be able to pinpoint what that looks like on the graph. The important thing is that the -22 is telling us what? What does this tell us about concave down? Okay, because it's negative, right? So concave down. So concave down looks like this, right? So if we know that at -5/3 there's a slope 0 and it's paired with concave down, what does that tell you about this -5/3 here? That there is a what? Relative max. So we say relative max at x equals -5/3. I see some students want to say that relative max is -22. Again, you just have to realize that number is hard to visualize. It is just a concavity value. If you want to find the y value, you got to go back to the original function. So we're not going to really know what that -22 looks like. We just know that it's part of a concave down shape. This is consistent, right? From our sign line, we got the same thing. Relative max at -5/3, relative max at -5/3. But the trouble spot is a lot of us want to say this is relative minimum because why? Because it's negative, right? We associate negative with something small, with something lower. with relative minimum, but this is not a low value. It's a curvature value. It's concave down. And because you have looking at concave down, you're looking at relative max. Okay. All right, let's test the other point, f double prime of 2. Again, this number is abstract, but what we do know is that it's what? It's positive. Therefore, my graph is concave up. If my graph is concave up, my graph will look like this. And at 2, there's a slope 0. So we have information about the slope. We pair it up with information about the concavity. We're looking at concave up. If it's concave up, we know we're looking at a relative minimum at x equals 2. And that's consistent with what we see here. So in the past, I see some students getting a little bit lost with the steps here, but I'm hoping that with an anchor process that you feel comfortable with, and then seeing how second derivative test is slightly different, that you can be convinced that this is true, and also a different process. All right, number 9. Sketch a labeled graph of the function with the following characteristics. So we have a bunch of information here. I think the best strategy here is create a slope and concavity sign line. And if you can create a slope and concavity sign line, then the arrows and the curves will help you kind of visualize what the actual graph will look like. Okay. So f of 0 equals f of 2 equals 0. These are just order pairs. I can just go ahead and plot these points on the graph. I don't need to put this on the slope sign line. These are just physical points on my graph. We'll kind of anchor my graph a little bit. The second and third statement will give me information about my f prime sign line. And then my third and fourth and fifth statement will give me information about my concavity sign line. So it says f prime of x is greater than 0. What's another way of saying that? Positive slope. Yeah, positive slope to the left of 1. So this is giving us information about a critical point there. So if they give us a boundary, then we can put it onto our slope sign line. So here's my slope sign line. They identified an x value for me, so I'm going to go ahead and place that there. F prime of x is greater than 0, so positive slope to the left of 1. Next statement, f prime of 1 does not exist. So what does that mean? Yes, so a couple things here. You can either make it, if a slope doesn't exist, it could be a number of things. It could be because of the sharp turn. It could be because it's a vertical asymptote. It could be a hole. So this is a very broad statement. There's a lot of room for interpretation. So you can interpret it however way you want, which means that your graph may look a little different depending on how you interpret it. Next up, f prime of x is less than 0 if x is greater than 1. What does this mean? Negative slope. Where? To the right of 1. Yeah, negative slope to the right of 1. All right, last statement, f double prime of x, second and fourth statement were all with the first derivative. The last statement is the only one that's with the second derivative. F double prime of x is greater than 0. What does that mean? Concave up. Where is the graph concave up? Everywhere except 1. So they are giving us information about x, so that's going to be your critical point there as well. So you can also place 1 onto your f double prime sign line. But it's concave up everywhere, so concave up, concave up. So because the third statement is so vague, there's different ways that you can do this. I'm going to draw this with a sharp turn, and then I'll show you what it looks like with a vertical asymptote, but you can draw it in both ways. So sharp turn, I have order pairs at 0, 0, and 2, 0. I'm just going to just draw this here without information. I just want to just do a very a draft because I know that this is not the final product. But I know my graph will have to rise until it hits some x value at 1, a relative max, and it's going to fall after that. This is my basic path of the graph, but I don't know exactly yet how I want the curvature to look, but I know that I've mapped out the path. Next up, I want my graph to be concave up in both sides of 1, and I want to make it a sharp turn here. So I'll make it concave up. I'm going to make it shaped like this. So concave up and concave up. Now, I don't want to continue and do a full U shape. Why is that? I mean, it's concave up, so why shouldn't I do a whole U shape? Why should I just make it like this? What's wrong with me doing it this way? Does that conflict with some other information that I'm given? Yeah. It doesn't, my slope should be always positive to the left of 1, right? So if I make it a full U shape, then I'm breaking the rule of making it negative slope, positive slope, negative slope, positive slope. So the fact that it's concave up and positive slope means that we're only going to show a portion of that curve shape. We're not going to do a full U shape. Okay. Let's go to page 5. Number 4. Have we done this yet together? No, okay. So this is page 5, number 4. It says if g of x is x cubed minus x on interval from 1 to 2, determine the mean value theorem. So mean value theorem is trying to guarantee a slope, right? So here's a formula for mean value theorem. It's where your average rate of change is equal to your instantaneous rate of change. So this is slope between the endpoints. This is the derivative. And then we set them equal to each other, and we can figure out where on the curve is the graph going to match the same steepness as what we experienced between the two endpoints. But we do have some conditions that goes along with mean value theorem. What are the conditions that we have to make sure we establish? There's 2 of them. Continuous and differentiable. So we want to make sure we state those out. There's no need to do any tests because it's a polynomial, so it's a smooth curve all the way through. But continuity is with brackets. Differentiable is with parentheses. Okay. Okay, this is what mean value theorem is. We know we can move forward because no issues with our conditions. So what does this tell us to do here? What should we find first? Slope, yeah. So what information do we need before we can find slope? Am I ready to find slope with just these numbers? What else do we need to find? Y values, right? And how do you find Y values? Plug it into the original, right? So we want to make sure we take care of the original portion first, stay away from the derivative, because what happens is if students do the derivative too soon, then you're going to start inserting the 1 and 2 into the derivative, and that's a wrong process. Right? So I know the reason why students want to do derivative first is because it just feels like an easier step to do. It's like, oh, power rule, that's easy. Let me get that out of the way. But do this part first. Okay, get the slope out of the way, and then you can work on the derivative, and then you can focus on solving. So let's find g of 1. Let's find g of 2. Find that slope. And we want to know what slope we want to target before we tell the derivative function what we're looking for, right? So we first need to know what we're looking for before we can give it to the derivative. Okay, what do we get? G of 1 equals what? 0. Okay. G of 2 equals 6. Okay. Slope, right? Change in y over change in x. What slope is this graph experiencing between these two endpoints? Slope of what? 6. So we know the 2 points. If we draw a line between the 2 points, there's a slope of 6, okay, which means that somewhere along the curve, this graph is going to experience an exact steepness of 6. And this is where the derivative comes in, and we can ask the derivative to tell us where the curve is going to experience a slope of 6. Okay. So now we can move on to the derivative side of things. G prime equals power rule. What do we get? Good. 3x squared minus 1. Okay, good. All right, now how do we involve the 6? Does the 6 get inserted into the x or someplace else? Yeah, this goes into g prime, right? Because 6 is a slope value. If you put the slope value in for x, then we're misinterpreting that information, right? So the slope value needs to go where the slope variable is, because we're asking the derivative to tell us the location of this particular steepness on the graph. And no need to do trinomial factoring. There's only x squared and constant. There's no x squared, x, and a constant. What's next? Take the what? Square root. What's going to show up if we do square root? Yeah, for equal sign. Yeah, so x equals plus or minus square root of 7/3. There's no need to rationalize the denominator. These are two different locations. So the graph has two different places where the steepness is going to be a slope of 6. But are we going to keep both these locations? Only what? Positive, because the interval, right? If something is outside the interval, we're not going to keep it. So the only x value solution is root 7/3, and what's the special letter to indicate that solution is C. It's just the x value solution for our mean value field. I'm jumping between problems because I want to go through the more challenging ones, and then hopefully you guys will be able to spend this afternoon and tomorrow, or tonight and tomorrow, working through the rest of the review worksheets. I have help sessions on the board, but I think I have one more problem that I want to do with you. This is on page 9. This is find critical points. Number 1. So what's our big picture here? if this says find critical points, we're going to do what? Find what first? Derivative, and then we do it with a derivative. Set equal to 0. But if there's a fraction, we have to set both the numerator and denominator equal to 0. The issue with this problem is that when you find the derivative, it's not going to be a nice clean fraction. We're going to have to condense that fraction, common denominator. Once we get that fraction nice and clean, then we can set both the top bottom equal to 0. Okay. So the challenge here for this problem is having to merge the two separate fractions into one before we can find the critical points. Okay, let's try that. Power rule. I got to subtract 1 from the exponent, right? So -1, which is the same thing as -5/5, which is what? Right, 3/5, right? Plus 3/5 x to the, what's the new exponent if I were to subtract 1 from this fraction? -2/5, right? Okay. Let me place the numerators and denominator where they go. So we want to find critical points, but it's harder to look for it without first merging the two fractions. So we need to find a common denominator. What's my common denominator? Well, something that both can multiply into. Good. Yeah. So you want something that is large enough that both can go into. 5 can obviously go into this. This is too big to go into this. So we want to choose the larger of the two. Good. So here is 5x to the 2/5. Just want to match common denominator, and then I want to balance each fraction. This one is between the old and new denominator. The old is missing the x to the 2/5. So I want to multiply the top by x to the 2/5. So if I multiply the two x's together, what do I do with the exponents? How do I merge these x's together? Add exponents, yeah. So if I multiply bases, I add exponents. 2/5 plus 3/5 is what? Just 1. Yep. 5/5 is 1. So that's just going to be 8x. Any adjustments here? Oh, same denominator, right? So just plus 3. So here's my f prime. All merged together. Now it's easier for me to look for my critical point because I have clean places to look for them. Set the numerator equal to 0, set the denominator equal to 0. Both are valid critical points. Okay, let's do one more problem here. Number 2. This is extreme value theorem. There's only one condition for extreme value theorem. What is that? Just what? Continuous, yeah. So my BC students, they just took a quiz on this, and a lot of them were putting continuity and differentiability for all the conditions, for all the theorems. Okay, so continuity and differentiability is only for something that is slope related, like mean value theorem and Rolle's. If it's extreme value theorem, it doesn't require differentiability. It only requires continuity. Okay. So extreme value theorem is just continuity. And we know it's continuous because there's no denominator, it's a polynomial. Okay. Now, the whole point of extreme value theorem is we want to find the highest and lowest points that sit on the graph. So our candidates come from f prime. But then once we find f prime, are critical points the only candidates we want to test for extreme value theorem? Critical points and what? Yeah, and the endpoints, right? So make sure that when you set f prime equal to 0 and you solve for x, that you don't just test those points with a function. You're also including endpoints as valid candidates. So let's try that. I get 2 and -1 are both valid critical points. They are because why? They're both where? They're both between the interval, right? Okay. So how many points are we gonna consider in total to test? How many points do you see that we want to test for absolute max and absolute min? 4, yeah. So 2 endpoints and 2 critical points. And how do we test them? Plug them where? A original, yeah, because now we're looking for physical locations. We want to know, hey, where are the y values so we can compare them. And in the end, you're only going to give me the y values. You'll say absolute max value is whatever the highest y value is. Absolute min value is whatever the lowest y value is. Don't give me order pairs. Don't give me x values, just the y values. But this is what happens, though. It's only going to say the word values. So on the quiz, some students will come up and ask me, do you want x or y values? And I'm just going to say to you, values. You have to decide whether it's x or y, or both. And it's just going to be the y values. So I know it's cryptic. Why not just say y values? But that's the way AP exam phrases it. So I want to prepare you guys for that. Okay, so all these values get plugged into the original function. You get to use your calculator. My lowest y value is -19. My highest y value is 8. So absolute max is 8. Absolute min is -19. Your homework, I want us to get some practice here. So your homework is just page 6. I'll send out a reminder. The key is on the next page there. Okay, come and get your phones. Tomorrow we'll start a next section, but it is kind of review, but it won't be on the quiz. But help sessions will be this afternoon, tomorrow morning, and Friday morning, and the quiz is Friday.